All right, recording is rolling. It is Tuesday, December 5th. We're going to knock out these textbook puzzles. The rest of the ones I assigned we hadn't touched yet. Earlier in class, that exactly took us to the end of the class. Tomorrow, we're going to do rotational inertia lab. Right. So let me preview this a little bit just so you have a day to sit on this and think about it. Right. I'm going to have you guys do an AP style write up too. Right. 5 parts. I'll have you guys score yourselves. Right. So rotational inertia. So like, what's the resistance to change in motion in a rotational sense? I'm going to set up this PVC pipe system. I think what I'll do is I've just I think last couple of years worked out pretty good. Is I'll set this up in the front. I'll guide you guys through this. Right? Have you guys fill out a table like this? Right? If you like rotate this pipe system, it's like free to rotate about the center. I mean, it's a tiny bit of friction, but not very much. Right? Okay. Then like, what's the resistance to change in motion? That's rotational inertia. And what we're going to do is wrap a string around the central pipe, which has this radial size r. That's going to be important. Right? Throw a weight over this pulley. The weight pulls down. Right? Now the tension in the string is a little bit less than the weight that's hanging down. Right? That idea you guys are going to see later today. We're going to recap that idea. Right? Now, if it accelerates pretty slowly, the tension's pretty close to the weight, but it's a tiny bit less. Right? And the more it's accelerating, the more slack in the tension. Right? But that sets up a torque, r cross f. But you guys know that torque is r cross f, but it's also I times alpha, right? And we're solving for I. That's what rotational inertia is, right? Capital I. Right? Rotational inertia times angular acceleration. So something to do with kinematic motion is angular acceleration. It's like speeding up spinning, right? So if you let this go, it's kind of like right. It's like speeding up spinning, right? That's angular acceleration. Right? Which maybe we could get from kinematic motion somehow. That's going to link back to maybe these guys right here, like solve for this alpha, one of these, right? Something like that. Okay. Hey, I wonder what tools you would need to bring this all together, right? R cross F equals I times alpha, right? Think about, I got a stopwatch here. Got maybe like meter stick going on here, right? Maybe I have to measure this radial size, right? Also, some of these variables are connected to each other, like the linear acceleration of this mass falling down and the rotational acceleration, the angular acceleration of this pipe system, right? Those are related to each other through this one right here. Right? You guys remember translating back and forth? Say like, have like a turntable. Here's angular acceleration, right? Speeding up spinning. Here's linear acceleration, like this falling. Right? They're connected by this r. Right? Now, where does this picture fit on this? Well, let's like make this little tiny cross section of a circle here. So this radius r is like this radius of this pipe, right? Which is not very much. It's like maybe a couple centimeters, maybe something like that. For exactly the measurement. We'll get that tomorrow. Okay. You guys got that? And then we're going to do an AP style write up. So again, just so you have a data prep for that, kind of think about what's coming your way, right? So 5 parts are thinking, right? It's going to be a question. The question is, what is the rotational inertia of this pipe system, right? That's what we're trying to answer. Right? So the conclusion at the end has to answer that question, right? Right? What measuring tools you're going to use, right? So think about that between today and tomorrow. What measuring tools would be necessary? Right? You guys know AP loves that question, and on the write up, you have to list some tools, right? Got a whole list of tools over there on that yellow look-on poster by that few data gathering procedure. All right, so you briefly describe the setup, right? So maybe I have this PVC pipe system, string around the pipe, pulley, weight, fall down, turn. Okay, so briefly describe the setup, maybe in a couple sentences, and then what did you use each measuring tool to measure each thing? I mean, you use this tool to measure this variable, this tool to measure this variable, right? Measure 3 times and take an average to reduce experimental uncertainty, right? Those are all parts you'll see in that, right? Analysis. This could go different ways depending on what's being asked. Sometimes you have to pull out an equation and use an equation to solve things to be analysis, right? A lot of times it's some kind of graph. In this case, it's going to be a graph. I'll show you guys exactly what the graph is. Torque versus angular acceleration. Because you guys remember torque equals rotational inertia times angular acceleration. That's tau equals I times alpha, right? And if you set this up as a graph, tau versus alpha, so that line up in a straight line, and the slope should be I, right? Kind of like y equals mx, right? Tau equals I alpha, right? That's like going in for the for the conclusion there, right? And in conclusion, rotational inertia equals some number of kilogram meter squared, right? I equals something to do with mr squared. All right, and then all right, AP Classroom Unit 7 debrief we did yesterday. We got pretty much exactly halfway through it. So the other half I'm thinking I'll save for Thursday, I think. All right, pretty good. All right, so you guys go with what we're doing? All right, so let's look at these puzzles. And I'm going to do something a little bit different today, which is, I think one of the best things that you do is like show you guys how to set something up, guide you guys through the thought process, and really a good thing to have, like especially for AP class, is independent practice. Right. So can you solve each one of these on a blank piece of paper from scratch? Right. So here's way we do this. I'm gonna flip my screen. Right. All right. So we're here. All right. Oh, what's going on here? Hold on. Let's pause this. Pause. Resume. Okay, we're back here. Share screen. That screen. All right. I think we're back ready to go. Right. So we did the 3 warm-up problems the other day. Right. Let's do the main set. So number 2 is the first one I circled. Find the net torque on the wheel. Okay, so we got this disc, right? It looks like it's rotating about the central point O, right? So there's like an axis into and out of the page, right? And 3 forces. It looks like this top force is pulling clockwise. This downward force is pulling clockwise, right? And this one on the left is actually pulling counterclockwise. You guys see that, right? Right. So I think there's a couple ways to interpret this that might lead to slightly different answers too, right? So it's R cross F is the torque, right? In different directions, you have to have some kind of subtraction. I'm going to call maybe clockwise negative and counterclockwise positive, usually do, right? Now, if these are all perpendicular to the axes, I can go just R cross F, and then R cross F, and okay, it's negative, negative, positive, right? And then deal, right? They're all perpendicular already, right? Now, that 12 Newton force, I see something about a 30-degree angle. Now, if you interpret that force as being perpendicular to this lever arm A, then the 30 degrees doesn't even matter. You just ignore that, right? Or if you interpret it as, say, 30 degrees from what would be perpendicular, then you need to bring in a cosine component, right? Let's see what I did for the solutions, right? With the solutions, I think I interpreted it as already being perpendicular, right? So that's what I did. Okay, we've got R cross F counterclockwise, and then minus R cross F clockwise, R cross F clockwise, right? So I got a total torque in Newton meters, right? If you had the other interpretation, you'd throw on a cosine of 30 degrees on that one right there, okay? So depending on how you interpret, okay, you guys get that? All right, next one. So that one, thing's pretty straightforward. Good warm up. Ooh, number 6 is pretty fun. I didn't circle that one though, but you want some extra practice, right? The next one is page number 11. I also did not circle, but I want to hit it real fast. Right, the center mass question right there, right? You guys did an empirical version of this, right? The foam board cutout. You guys found different ways to find the center mass, right? Now let's do the mathematical version. Now, I did not circle this one because AP would not ask this question, right? But I think it's good. So it's this. Like, what's the center mass of this plywood sheet? Right? So if this is like uniform density, like a flat piece of plywood, right? Then we can play off the areas to get the center mass, right? You guys remember center mass is like a weighted average type, right? And the way I set this up in the solutions is I split this into 2 parts. I said, well, we got this big old rectangle on the left side, which has an obvious center mass, maybe right, bam, like right there. And we got this small rectangle on the right side, which center mass would be like also the geometric center if it's evenly distributed, which is bam right there, right? So I wanted a weighted average between like these 2 centers of mass of these 2 rectangles. Like if I have big rectangle there and little rectangle there, right? That's exactly it. So let's go scroll down to number, here it is. Here we go. Here's your X bar and your Y bar. Now you have to find the center mass for both the X coordinate and the Y coordinate, right? And the answer is going to be a coordinate, right? So the way I set it up on the poster is it just did along one-dimensional axis. So we have to do X and then Y, right? So here's like the average for the X value. I played off the areas, right? So the 16 I left is unitless, but maybe this is like an area, which would correspond to some mass, right? If you multiply by some density, right? Kind of left that ambiguous bit, right? Anyway, the X coordinate average ends up being like this right here, and then you do the same thing for the Y average, right? You take like weighted average, right? So mass times location plus mass times location divided by the sum of masses gives you the average location, right? You get an average Y coordinate, average X, average Y. Let's go back to the picture and take a look. So 3.33 in the X and then 1.67 in the Y. 3.33 in the X, bam, 1.67 in the Y, bam. It's like right about there. That point right there where my cursor is, you could balance it on your finger. Yeah, that looks about right too, right? It's a good thing to do in physics, right? Check your answer after that, stand back, does that look like it makes about sense? Yeah, that pretty well does. The balance on your finger, right about that point right there. Okay. Right. Weighted average. Right. This next one I did circle. We got a hungry bear with a weight of 700 newtons walks out on a beam. It's only a small bear. In an attempt to retrieve a basket of goodies hanging at the end of a beam. Ooh, look at there. The beam is uniform. So that means its weight is evenly distributed. That's embedded in that word, which means that this weight of 200 newtons for the beam, we can treat as acting at the center of mass of the beam, right? Okay, here's the length of the beam, supported by a wire at 60 degrees from the beam, right? Draw a free body diagram. Well, it says force diagram, so same idea, right? And then when the bear is at, say, like 1 meter over, right, what is the tension in that supporting cable, right? And then another question, right? If the tension can go up to some value, then how far out can the bear walk? Okay, because as the bear walks to the right, you guys think the tension is going up, 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 right? You set up like a torque equation to answer that, and then set the tension to the maximum tension. And there's going to be some location the bear can go from that pivot point, right? You said, right? Now, I gave you guys a simplified version of this a few days ago as a starter question. So if you're looking at your notes from a few days ago, like, oh, okay, this is just kind of an extension of that, right? Let's look at my solution for this one. Oh, there we go, right? No, okay, so here's the beam right here. I put forces at location. So here's the weight of the beam, boom, 700 newtons right there. It's some generic distance x, so we could like solve for that or change that variable. Here's the weight of the beam. Now I'm treating the weight of the beam acting as its own center of mass, which is also the geometric center. So it's like half of its length. Right? Here's the basket of goodies, has some weight. And then here's the cable. Now I did make these solutions a few years ago. I have to go and clean these up a little bit, update these, right? But here's how I would make this a little bit different. I would draw this a little bit differently. I would draw the tension as just a solid vector, and then I would dash the components, right? That's how we do it nowadays, right? Now, the time I made this, I didn't know AP convention for this, so I scratched out the original and replaced it in terms of the components. You guys are going to dash the components, right? Otherwise, AP is not going to give you credit for a free body diagram. I would go dash, 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 right? Right. So anyway, that's all right. Also, at the hinge point, there's a couple of forces too, or maybe a single force that has components, but I drew it as two separate forces, right? I think that this cable, think about this cable, is pushing this beam into the wall, and this wall is pushing back with some F sub x, force in the x direction. Also, this cable's pulling up, and there's a bunch of weights down. There's like 3 downward weights, right? I bet there has to be an upward force at the point of the hinge. That's an upward, that's F sub y. So that's kind of like 3 unknown quantities. I don't know F sub x. I don't know F sub y. I also don't know this tension. That's like 3 unknowns. Ooh, that sounds like a bunch of equations I have to set up. Or do I? All right. Now here's 3 equations that apply. Here's for equilibrium. X direction forces 0 out. That means however much the cable is pushing the beam to the left, the wall is pushing back the same amount. That satisfies that equation. The sum of the forces in the y zeroes out. That means the 3 weights down, 1, 2, 3, have to be balanced by 2 upward forces. So this F sub y upwards, and this vertical component of the tension have to zero out. Right, and then the torque also zeroes out. Now, you guys had a 2-day lab on torque, and you guys had a seesaw version. You guys had a scaffold version, which actually looks pretty similar to this. And I was telling you guys, you could sum the torque about any point, it would always zero out. I could pick this point, this point, this point. I could pick a point off the system, like over here. The torque still zeroes out. But sometimes there's either a most intuitive point to sum the torque about, which would probably be this hinge point, and sometimes there's a mathematically convenient place to sum the torque about, which happens to be the same point. Here's why where my cursor is right here is a really good point to pick the like as a pivot point. Besides, it's probably the most intuitive anyway. Right? These 2 unknown forces, F sub x and F sub y, cause 0 torque themselves about that very pivot point. Right? Like if you push on the hinges of a door, it doesn't cause any torque because there's 0 radial distance from that point. So in terms of a torque equation, if you pick this as your pivot point to sum the torque about, those forces immediately go away. And now you're down to only 1 unknown. So yeah, that's what I'm looking at. There's a huge opportunity right there. That guy right there. Sum of torque goes to 0. I can set up an equation with only 1 unknown. And the only 1 unknown would be this tension right here. Right? Right? You guys see that? That's a good roadmap, right? And then later on, if you wanted to go solve for those forces, you could, right? With those other equations, maybe, right? Right. So here we go. Where's the setup? All right. So here's the sum of the torque. Okay, I should have. All right. See where it says sum of torque is 0 Newton meters, right? That's like the first step, and then the next step is you set up clockwise and counterclockwise torques, and there would be 4 torques, right? The weight of the bear says let's go clockwise. The weight of the beam says let's go clockwise. the weight of the basket of goodies says let's go clockwise. And only the tension is holding it back counterclockwise. But really, it's the sign component of the tension, right? Just like the starter question a few days ago. You saw that? It's this vertical component because that's perpendicular to this radial arm, right? It's T sine theta is providing the counterclockwise torque, right? And that's at the radial arm, which is the length of the beam itself. All right. Now, I went ahead and skipped on to the next step, which would be to add that over. So you got T sine theta times the length of the beam. So there's R cross F right there, right? That's saying let's go counterclockwise. That has to balance out with the other three torques going clockwise. R cross F, R cross F, R cross F. You guys see that? Right. There's only one unknown. You do a little algebra, boink, solve for that, you get that many newtons right there. There's the, okay, that's the tension in the cable. Right. Again, important thing is, can you see a big picture how to set that up? And then right later on, like tonight, pull out a piece of paper, see if you guys can, from a blank piece of paper, solve that all from scratch. Okay. There was another question, which is, suppose the maximum tension is like this many newtons, okay, which is more than the tension from before, right? Which means the bear can still keep walking towards the basket of goodies, but at some point that cable's gonna snap, right? So it's the same setup. Look at that, it's the same setup. All I did was I plugged in the now known value for tension, because go ahead and let that go to the maximum value. And instead of the bear being at 1 meter, well, now let's replace that with some general x. But otherwise, everything's the same. You guys see this setup here from last question, this setup here, right? And now you solve for x, you get a value. That's how far the bear can walk out. And the bear walks out exactly that far. Now the cable's right at the point it's about to snap. Okay, all right, you guys get that? This right here. I think I did 6 meters times sine 60 degrees. Let's see if that's what I did. 6 sine 60. Yeah, right. I pushed these two guys together. This and this. Okay. It's a little different way to looking at it. Okay. Right. Yeah. All right. And then the units meters. All right. There we go. All right. Let's see what I got next here. Expected here. All right. The next one is a circled question. Right. Oh, this is kind of a geometry type question. I like this one. Right. Refrigerator with some width and some height rests on an incline, and there's static friction, which means that you can tilt it and it's still stuck to it. Right. But at some point it's going to topple over, right? If this angle is too big. So what angle would make it topple over? Now, this is really a geometry question. And so where's this detail? Okay, this last line says treat the refrigerator as a uniform box. Right? That's important so that you can say the center of mass of the refrigerator is also the geometric center, which is right about here. Right? Actually, they drew it pretty good because if you have the center mass like right above the base of support, here's the base of support. Right? As long as the center mass is above the base of support, it's going to be stable. But if it's outside the base of support, it's going to topple over. Have you guys ever done this challenge where you put your back against the wall and you have your heels against the wall? So everything against the wall, right? You try to reach over and touch your toes, right? Really hard to do. Now, some people can do it, right? But it's really hard, right? Because now if I was standing out in the middle of the room, it'd be easier because I can like back up and keep my center mass over my feet, which is my base of support. But if I had my back against the wall, right now I can't do that. Now my center mass is gonna go beyond my toes and I'm gonna topple over just like this refrigerator, right? Right, so switch my screen back over here. Talking about a stability type question. Right? I doubt AP would ask this, but this is one of those things that's good to pick up extra from this class, right? Something like this, right? What's stable or unstable? Ooh, I also did turn this into an official poster last night too, but haven't printed out yet. Okay? So if any small deviation causes it to like accelerate, fall down, that's unstable. If any small deviation, right? Like here could be place this pyramid with a fridge. If you like started pushing the fridge over, it would actually have to raise the center mass. You have to do some work to do that, and then it would just fall back to its original spot, right? Unless, of course, you tip it to the point where the center mass is just above the edge point of the base support, right there, right? But this is geometry, so I think I could look at this right triangle right here. I could say this angle is equal to this angle, and then say theta is equal to, or I should say, tangent of theta is equal to W over H, right? Width over height. So tan of this theta right here. Oh, let's look at my solutions. I think I got a nice picture of this. There you go. See that dashed line right there? Right. So tangent of that angle theta is W over H. So the next step would be inverse tan both sides. So theta is inverse tan of W over H. Right, you guys can figure that out. All right, guys good? Yeah, it's right there. It's right there. Right. So you're doing geometry. Tangent of the angle is W over H. Therefore, therefore theta is inverse tan of W over H, right? And that's the critical angle it's about to topple it. All right. All right, guys good? Guys good? All right. All right, next one. Okay, so that one looks pretty fun. That could be a good challenge if you want to try that one out. The next one I circled is number 35. All right. Now, this one we're about to do is related to tomorrow's lab. So a rope of negligible mass is wrapped around a 225 kilogram solid cylinder with radius 0.4 meters. Right. Already I'm thinking, I remember from that rotational inertia table, the rotational inertia of a solid cylinder rotating about central axis is like 1/2 mr squared, right, per solid cylinder. I think that's what they're setting up here. There's M, there's R. Okay, put it all together. The cylinder is suspended several meters above the ground. Its axis is oriented horizontally, so it turns on its axis without friction, right? A 75 kilogram man takes hold of the free end of a rope and falls under the force of gravity. What is his acceleration? Right now, it would be free fall, except that this cylinder has inertia, right? So it'll slow him down, so he's not going to fall at the full rate of gravity, right? What is the angular acceleration of the cylinder? Right. Well, if you know A, you can get B because there's a kinematic. Well, there's a connection there, right? So linear motion to rotational motion has something to do with the radius of that cylinder. And then, okay, and there's a question C, but we'll save that one later, right? Let's look at the. You know what? Before I go to the solutions, right? Can you guys imagine what this is going to look like? Right. Actually, there's a similar type question coming up. Probably a pretty good picture, right? It's kind of like you guys see this picture down here for number 52. It's a very similar picture, right? Got a cylinder, rope wrapped around it. It's kind of free to rotate. Instead of the bucket, it's just 75 kilogram guy, right? Right, pulling down. Right. Wouldn't his weight be like 750 newtons? Right. Now, what is the tension on the rope? If he's at rest, the tension is also 750 newtons. But if he's accelerating, it's got to be less than that, right? And that's the challenge question that I want to throw at you guys. So here's some review from Unit 2, which is way back. Right. If here, I'm gonna switch my screen over and maybe ask you guys something you can solve for here. Right, you guys ready for a good review question from Unit 2? Right, right. So here's like the cylinder with the rope wrapped around it. Here's this guy. Right, hold on, and he's gonna be falling down. Right? Now he has some. He has two forces on him. I'm taking two forces. Right? He's got a weight pulling straight down. There's your mg. Right, and he's gonna be accelerating down. Right, this is an accelerating situation, right? But it's not pure free fall. Right? I'm thinking there's a tension upward. What does the tension upward look like compared to his weight? Is it same size, larger, or smaller? Smaller. Yeah. Maybe I'll just call that T for tension. I think in my solutions I went capital T for tension. Got that, right? So, some version of that, right? Right. Now, what is this acceleration in terms of all this? Or for that matter, if you knew acceleration, you wanted to solve for tension. We're going to bring acceleration somewhere in here, right? Can you guys set up an expression? Go ahead and do that right now in your notes. Set up an expression for what is the relationship between these two forces, the mass of this guy is m, and his downward acceleration. He is going to be accelerating downward. There's a net force downward. That's A, right? How are that, and that related to each other? Okay. Go ahead and set up an expression. Set up an expression. Okay. Here's a hint. That looks like elevator physics. You guys remember if you're in an elevator accelerating up or down, right? It's essentially the same setup as this guy hanging onto this rope, right? Think about elevator physics. Right? All right. I would walk around the room, but I think it's going to be a tight fit. So just give you guys a head start. Did you guys say Newton's second law of motion, net force equals mass times acceleration? Right? Or you could call this like the sum of forces if you want to. Sum of forces. Goes mass times same thing. Sum of forces, net force, same thing. Right? Right. Then if I call down the positive direction, it looks like there's a lot of stuff down. You move down, accelerate down. That'd be the weight down minus the tension up. Isn't that the weight down minus the tension up results in mass times acceleration? Right? There you go. There's a relationship right there. Right? Right. Let's go another step. Can you solve for tension in terms of everything else? Tomorrow's lab, this is going to be one of the steps. Right? Maybe I'll have you. Okay, something. Right? We got to figure out what is the tension of string tomorrow. Right. Did you guys say tension equals mg minus ma? Right. If you like, you can factor out the mass, G minus A. Oh, look at that. That should look really familiar because you guys have seen this a few times. I know it was a while ago. It goes back a while, but you guys have definitely seen this a few times. Okay? So if he's not accelerating, if he's either at rest or moving at constant speed, acceleration 0, then the tension is just equal to his weight. Okay? If he's accelerating at pure free fall, right, then G minus G is 0, there would be 0 tension. And then realistically, it's probably somewhere between those two boundary conditions, right? Like I said. Right? All right, so let's switch back over here. I wanted to do that before I flash over to the solutions because near the top of the solutions, I have that written down, but I didn't actually derive it. I just said, oh, remember this? All right, so here, we're on number 35. Let me find the solutions here, number 35. Okay, oh, okay, there's your cylinder. It's got some mass capital M, it's got some radius R, and there's, from the point of view of the cylinder, there's a force that is the tension, right? Oh, I made a note over here. The tension is not the same as the weight of the guy, right? That might be an easy mistake to make. You guys know the tension is going to be less than the weight. In fact, it's, look at this dashed outline expression right here. That's what we just derived. That's why I did the challenge question, the review with you guys, because that's right there, right? Right. So the tension of the string is the mass of the guy times G minus A, right? And now let's go set up torque, right? So the torque that's causing this thing to speed up spinning, that's called angular acceleration. That's R cross F, right? Torque is R cross F, right? But the force is the tension. So that whole expression is going to substitute right there. Right? Now, torque is also I times alpha, rotational inertia, which is probably like half mr squared, I think, for this guy. Oh, okay, I have that right here, ready to substitute in. Right? And then alpha is angular acceleration, which is linear acceleration divided by the radial size, right? You guys see these 3 dashed outline expressions are going to all substitute into this, right? So here, we got a bunch of things going on here. We got like 5 different things going on, right? Torque is R cross F. That's like the wrench opening a door. Torque is also I times alpha. That's like Newton's second law of motion, but in a rotational context. And then a bunch of these bits have substituted values. So force is the tension, which is mg minus a, substitutes there. Rotational inertia of the disk, because it's a solid cylinder, it's like 1/2 mr squared. Right? And then angular acceleration is a over r, substitutes right there. Right. All right, let's switch back over here to remind you guys a couple things there. Right. Where's the 1/2 mr squared come from? It's coming from this table. You do not have to memorize that. AP will not expect you to memorize that. If they want you to do a calculation, they'll give that to you. Okay, right? But good to know that's there. That's where it comes from. If you're a little bit of interest, maybe you'll study that. Know that. Right? Where's the connection between linear acceleration and rotational acceleration? Oh, that's right here. Right. So I did the version where I divide the r over and get a divided by r is equal to alpha. Right. Okay. Very good. So we're putting that all together. Okay, are you guys okay with where all those individual bits come from? Right? Because once you get that, you're past the hard part. Oh, it looks like all the radius cancels. Look, here's the next line. Here's with all the substitute values. That R, they're all the same. They all interesting, they cancel. So interesting if you had a larger radius cylinder, but it was like the same mass, maybe it's like different density material, right? That ends up canceling out in the end. Right, interesting, right? And then, and this acceleration is this acceleration. Okay, that's why I did this substitution right here in the first place. Because this A and this alpha are related to each other, right? They're not independent of each other. So you make that substitution. Now you can compare those two, right? So you can pull that over and solve for it. Ends up being this expression right here. Now this is in terms of variables, which is a good skill to have. I like to solve in terms of variables. I guess you can plug in numbers at any time, but this is like the master answer. Okay? So it looks like the weight of the guy divided by his mass plus half the mass of the cylinder. Right? Again, the radius cancels out, so that's not part of the equation. So boom, just like that. And you get, there's the linear acceleration right there. Right? Guys, what's the smallest number that the number in this box could possibly be? 0. Right? That's if you had an extremely massive cylinder and an extremely small guy. Right? What's the largest number this boxed value could be? Maybe like, I guess 9.8 meters per second squared, right? Is what I plugged in, right? That's pure free fall. That's if the guy's extremely heavy and a very small mass cylinder. Okay. So it's like the boundary conditions, right? And this is kind of somewhere in the middle, right? Oh, okay. There was a part B, which was what's the angular acceleration of the disk? Well, once you know the linear acceleration of the guy, you just very simply divide by radius to get angular acceleration. Boom, right? I think it's a complete coincidence. This number looks like the gravitational constant, although it's not. It's completely different units. It's just coincidence that the number happens to be 9.8. Okay, that's radians per second squared. Right, it's the speeding up spinning. Right. Oh, there was a question C. Question C. Okay, let's go read question C. First of all, you guys okay so far? You guys okay so far? Everybody right? Right. Okay. If the mass of the rope were not neglected, because almost all the time in here they say, "Oh, negligible mass string or negligible mass rope." No, that's not the case. What would happen to the angular acceleration of the cylinder as the guy falls? This looks like a good conceptual question. I think this would also be a good opportune question from AP. I think AP could ask that question. I think that would be fair. It would be plenty fair, right? So let's get a picture going and imagine this. Right. Now the mass is not negligible. Right? So now we got a rope wrapped around that has significant mass. Right. So I remember torque equals R cross F, which equals I times alpha. Right. And the question is, what happens to alpha if we change the scenario to having this rope with significant mass? Right. Is it correct? Right. Now it's actually going to change. I think a couple of things here. Right, let's go piece by piece this equation, right? So R, does the radial size of this disc change? Does the R change? No, that's pretty well locked in place. Well, I don't know. Let's say that stays the same, right? Right. Does the force pulling, does the tension change? Does the force pulling down change? How many say it does? Yeah, and it would do what? Guys, as there's more and more rope, this rope gets longer and longer, and it is massive. It has weight. Is that force decreasing or increasing? Increasing. This is going up, right? Now, in isolation, that alone would cause alpha to also do what? Increase. I see a direct relationship. If it's like twice the weight of rope, or like twice the force, you'd be like twice the angular acceleration. Is that? But that's not the only thing that changes. As the rope is leaving this turning cylinder, is what's rotating up here getting more or less massive? Less massive, because the rope is leaving it. Therefore, what's happening to the rotational inertia? It's decreasing at less mr squared. And that has an inverse relationship with alpha because they're multiplied together, which also causes alpha to do what? Further increase, right? Like if you have half the I, you have double the alpha, right? So there's two effects that are both causing alpha to increase, right? Guess that? So for two reasons, is speeding up even more, okay? Right. Now, in this class, usually you assume uniform motion, which would be like a constant alpha, right? That would go hand in hand with like a massless rope, right? But yeah, that wouldn't be the case if you consider mass rope, right? But that's a good conceptual question, right? Kind of hard to do math on that, but yeah. All right, there we go. Right. So you guys good with that? Good with that? All right. What was the next one I circled? Here. Number 52, right? Which actually looks really similar to what we just did. Let's go on here. Okay. Look at there. Bucket, cylinder, free to rotate. Right. Now here's the difference. The premise in the question, right? The first line says use conservation of energy, which if you think about it, is something that we did not do in the last one, right? They're really giving you guys a big hint here how to solve this, right? I want you guys to see big picture, like 1,000-foot view of like why this is a really nice hint, right? Look at what's actually being asked to determine the angular speed of the spool after this 3-kilogram bucket has fallen 4 meters. Ooh, right? So a few things. We're asked to solve for angular speed. The previous question, which had a very similar setup, you could use the same picture basically. The question was something about acceleration, which was a good setup for torque, right? Torque equals I times alpha, you get alpha, switch over, solve for A, right? Maybe we want to use like dynamics for that. Right? But whenever you're asked to solve for speed, that's a hint that maybe energy is a good method to solve for this, right? Right. There's another hint that conservation of energy would be a good method to solve for this, and that's the fact that you're given a falling distance rather than a falling time. You guys remember all those conservation of energy equations? We never really had time as a variable. There's like potential energy, I don't see time there. Kinetic energy, don't see time there, right? Right. But there were like falling distances, like that matter. Right. So let's see again. Let's make a connection between the last question and this question. Right? Do you think you could, in principle, use conservation of energy to solve number 35? Yeah, you could, but it'd be a much longer process, right? You could solve for some speed after some falling distance, and then go back to kinematic motion and figure out acceleration based on that. That would be a really long, convoluted process, right? Opposite side of the coin, this question number 52 with the falling bucket. Do you think you could, in principle, use torque to solve for acceleration, and say fell some distance, use kinematic motion and solve for final speed that way? Yeah, you also could. It'd be a long, convoluted process. The fastest way to solve it is exactly how they're suggesting it: conservation of energy. Okay, right? You guys see? Right? Because in physics, sometimes multiple ways to get to the same answer. Right? Okay. And hopefully, you guys are making these connections. Say, okay, I could solve it this way. I could solve it this way. This way's faster, right? And here's how I know it's faster, right? Okay. Here's it. So go ahead in your notes right now. Write a conservation of energy equation that's going to kickstart this whole process before I switch over to the solution and point it out to you guys. Okay? So I'll give you guys about 30 seconds here. Set up a conservation of energy equation that could answer that question. Oh yeah, okay. And then we'll flip over and see how you guys did. Okay, conservation of energy. Conservation of energy. Right. Right. So you guys said sum of energy initial equals sum of energy final. Right. Okay. I bet most of you guys got it by now. So, guys, what's the supply of energy? What type of energy? Yeah, gravitational potential energy. The fact that this bucket can fall, in this case, 4 meters is the height that it can fall, right? Right. And then after it's fallen 4 meters, it's in motion, right? It's in motion, right? And what kind of energy is that? Kinetic. Now the bucket's falling down, that's linear kinetic. Hey, is this wheel also turning? And what's the expression for that? Rotational kinetic, right? Right. Let's look at the solution, number 52. 52. Oh, you know what? One we skipped along the way. Oh, look at that. It's the roll race. Hey, it's the original version of the roll race. Right, we're past that. 52. Here we go. Sum of energy initial equals sum of energy final. Right, that was what they said to use. Right? Hey, look at that. The bucket can fall. That's supplying the energy, mgh. And he goes into, hey, 2 places. 1/2 mv squared for the falling bucket, and 1/2 I omega squared for the rotating disk. Right? Now, those two concepts are not independent of each other. This v and this omega are connected. In fact, they're connected exactly by v equals omega r, or you could switch the other way around. You could go omega is v over r. Whoops, switch my screen to for the video. There we go. Right. Think about this right here, right? This line right here, right? Right. So if you wanted linear speed, you would substitute out omega. If you want angular speed, you substitute out the v, right? Which is what was asked. They said, what's the angular speed, right? Like how many radians per second is what we're looking for. So I'm going to substitute out the v, and back to here. That's exactly, bam, what you did right there. You can see that's going to substitute right there. Right now we can have some omega that we can compare. That omega is that omega in the next line, right? While I'm at it, let me go ahead and substitute out the rotational inertia of the disk. Right, I know from a rotational inertia table, it's 1/2 mr squared, where m is the mass of the disk, not the bucket, but the disk, right? Because that's what's rotating, right? Raise the bucket, boom, substitute. Right. Now, here's the mass of the bucket, here's the mass of the disk. That's 2 different masses, lower m and capital M. Right? That omega matches that omega, bam. That r matches that r, bam. Right, now we can, I guess, factor some stuff out. Okay, here's omega in terms of variables, right? Mass of the bucket, mass of the disk, right? We got that. Right, and if you plug in values, you get a numerical answer. And the question was omega. Okay, that's what's set up to solve for is omega. Right? It works out to that many radians per second. Yeah. Factor the r out. Yeah, you can do that too. Yeah, you can factor out the r squared from. Yeah, you can do that. You can do factor out the r squared from here, and then I guess since it's under the root, you could do 1 over r. You could bring it out in front too. Yeah, that'd be another way you could do it. You could do 1 over r out in front and get rid of it on the inside. Sure. Right. Yeah. Oh yeah. Instead of 1/2 mv squared, you do force resistance. Let me think about that. Instead of 1/2 mv squared. Okay. Well, that's kind of what this is right here. Here's well, I think about that. I have to think about that. Did you get like exactly the same? Huh. Well, if you used a larger value for gravity, then it should, I think, be spinning faster. Would it be? I have to think about that. Right. I know this works though. The setup. Right. So there we go. Right there. Conservation of energy. What, I feel like I want to say something else. I forget what though. Right. Okay. Well. Okay. See what's next. Ooh. Okay. So next one is this guy right here, number 63. Okay. So here we got a puck on a frictionless table, they say, so the air hockey table, and there's a hole in the middle and there's a string, and it's like moving around in a circle on that dash line path, right? You kind of get that from the figure anyway. Well, it says the same thing here. Right? They attach some numerical values, right? Right? And you're holding it in place. Guys, doesn't this look a lot like your centripetal force lab with the Play-Doh canisters and the PVC pipe and the string? In fact, there was a textbook question that also had a very similar looking picture, right? Right? There's some mass, some speed, and then like some force you have to pull that, right? Right. So the puck in the figure has this given mass. The original distance from the center is so many centimeters. Right. In the back of my mind, I'm thinking, if I want to do any math, I probably want to convert that to meters first, right? Like 0.4 meters. Right? It moves with the speed of, let's call that 0.8 meters per second. Right. The string is pulled down 15 centimeters. Let's call that 0.15 meters. Right. Through a hole in the middle of the table, frictionless table. Determine the work done on the puck. Hint: consider the change in kinetic energy. Right. So let's go over this verbally, and then switch over to the solution. Right. It's kind of a two-part problem. Right? Like, how much work does it take to pull down? Right. I mean, it would take some work, right? Because you imagine pulling on that string, you'd be putting some force times distance to pull it down, right? Now, if you do that particular method, force times distance, it's actually kind of convoluted because I don't think the force is even constant, right? The thing is, you pull it down, the force changes, right? So if you follow this hint at the bottom, that's like the cleaner way to approach this, right? The change of kinetic energy. Okay, so there's some original kinetic energy, 1/2 mv squared, and as you pull it down, the radial size of this thing changes. So there's going to be a different 1/2 mv squared. The linear speed changes, right? As you pull it in. Now, how does linear speed change, right? And that is going to actually set up the first half of the solution, which is that there's a conservation principle going on here. Guess what is being conserved? Conservation of what? It's not energy, it's angular momentum. Conservation of angular momentum, right? You guys remember like the ice skater, like pulling their arms in would speed up spinning, right? Because angular momentum was conserved. A similar thing here. When you pull the puck in, all right, it actually speeds up. So let's check out this is number 63, right? 63, right? Right. So I have to speed this up a little bit because we're getting close to the end of class, but we got I omega equals I omega. There's conservation of angular momentum right there. Right. Boom. Here, should have written that first. Right. And then I substitute mr squared for a point mass for the puck. Boom, boom. Omega is v over r. Boom, boom. Oh, hey, look at this line. MVR equals MVR. Now, I gave that to you as a fact that angular momentum of a point mass was MVR. But here it is kind of derived. Look, it's derived right here. Starting from I omega, right? Plug in values, you get the new speed. All right, but the question wasn't about speed. The question was about work, and they gave you a big hint. They said it's the change in kinetic energy, which is right here. So here's part 2, right? Change in kinetic energy is the work done. It's difference of 1/2 mv squared. The mass stays the same, obviously, but the speed change, right? Works out to this many joules. If you like, call it many millijoules. Okay, right, guys, that. All right, let's see if I can fit this in for the bell. All right, got one left. Right, I want to along the way and passing, if I can, real fast mention. Number 64 is a fun one. I used to sign it in the past. I didn't, you guys, but if there's a giant rotating O'Neill cylinder and a bunch of crew members go to the conference table on the inside, that's like the ice skater pulling your arms in. So this whole thing speeds up spinning. And then the extra fun is if you were left on the outside, you would feel heavier because it's spinning faster. How much heavier? Okay, so have fun with that one if you want to take that on as a challenge, but I didn't circle that one. The last one I did circle is this right here. Hey, this looks a lot like your torque labs, doesn't it? Right. So they told you what is force 1 and force 2, like springs are compressed. They told you the weight of this bar. This bar has a weight. They say what's the force and also what's the location of this other spring. Once you know F1 and F2, like these two forces down here, it becomes exactly determinable of not only what is the force that's top spring, but also where is it located. There's only one location it could be that corresponds to these two other given values. Right? Turns out this top spring happens to be in tension for this particular question because this is a very heavy bar, right? So you can use, you guys remember equilibrium? Not only do the sum of forces sum to 0, but the sum of torque sums to 0. And you have to use the torque condition to be able to answer this question, okay? So I might pick like this point on the far left, for example, and say, clockwise and counterclockwise torques. You can also separate equation to say the forces sum to 0. This number 75, right? We flip down to the solution. Oh, skip right past it. Right here. The forces sum to 0, right? But that's not enough to solve it by itself. But well, you can get the spring force, right? So it turns out to be in tension, right? But if you want to figure out the exact location, you have to bring in the torque sum to 0. I pick the far left point, sum the torque about, boom, get location. All right, in time, we got them all in. All right, so you guys have a great day. Think about this lab tomorrow. I'll have you guys do a write-up. Yeah, tomorrow's lab day. Oh, yeah.